and starting methods of induction motors. Sound control. You can use this to adjust the volume setting for this module. Previous button. Click this button to go to the previous slide. Next button. Click from here. Click Next to continue. Pre-assessment. By the end of this module, you will be able to list different losses in three-phase induction, compute efficiency of three-phase induction, list different faults in induction motor, differentiate between concepts like crawling and cogging, and explain different starting methods of three-phase induction motors. Click Next to continue. There are several losses that occur while induction motor runs, which are categorized as follows: fixed or constant losses and variable losses. Click each to know more. Fixed or constant losses are further of three types as follows. 1. Iron or core losses. 2. Mechanical losses. And 3. Brush friction losses. The most important of these are iron or core losses. Click iron or core losses to know more. Click this arrow to know more. Iron or core losses are further divided into hysteresis and eddy current losses. Eddy current losses are minimized by using lamination. Iron or core losses are further divided into hysteresis and eddy current losses. Eddy current losses are minimized by using lamination. Since by laminating the core, area decreases and hence resistance increases, which results in decrease in eddy currents. Hysteresis losses are minimized by using high-grade silicon steel. The core losses depend upon frequency. The frequency of stator is always supply frequency, F, and the frequency of rotor is slip times the supply frequency, SF, which is always less than the stator frequency. Hence, the rotor core loss is very small as compared to stator core loss and is usually neglected in running conditions. Click Next to continue. These losses are also called copper losses. These losses occur due to the current flowing in stator and rotor windings. As the load changes, the current flowing in rotor and stator winding also changes, and hence these losses also changes. Therefore, these losses are called variable losses. The copper losses are obtained by performing blocked rotor test on three-phase induction motor. Click Next to continue. Click Next to continue. Since we are aware of the losses that occur in induction motor, let us understand how they impact the efficiency. Before that, let us learn what is the efficiency of induction. Efficiency is defined as the ratio of the output to that of input. Rotor efficiency of the three-phase induction motor is the ratio of gross mechanical power developed to rotor input. Three-phase induction motor efficiency is given by the ratio of power developed at shaft to the electrical input given to the motor. Click Next to continue. The journey of power from input to output is long and interesting. Click Power Flow to know more. There are a number of losses that occur while power flows from input to output. Click each blue text to know the formulas. Click Next to continue. There are several faults due to which the motor gets burnt or damaged as follows. 1. Overload. 2. Unbalanced voltage. 3. Single phasing. 4. Over voltage. 5. Under voltage. 6. Earth fault. 7. Short circuit. 8. Prolonged start. 9. Stalling. 10. High ambient temperature. 11. Inadequate lubrication. 12. Wrong alignment. 13. Excess vibration. 14. Anomalies in cooling. Click Next to continue. Let us now learn two important concepts called crawling and cogging. Click each to know more. Click each icon to know more. It has been observed that squirrel cage type induction motor tends to run at very low speed compared to its synchronous speed. This phenomenon is known as crawling. The resultant speed is nearly 1/7 of its synchronous speed. This happens due to the fact that flux produced in the gap of the stator winding because of odd harmonics like third, fifth, seventh, etc. create additional torque fields in addition to the synchronous torque. The torque produced by these harmonics rotate in the forward or backward direction at ns by 3, ns by 5, ns by 7 speed respectively. The torque produced by the fifth harmonic rotates in the backward direction. This torque produced by fifth harmonic, which works as a braking action, is small in quantity, so it can be neglected. Now the seventh harmonic produces a forward rotating torque at 1/7 of synchronous speed, ns by 7. Hence, the net forward torque is equal to the sum of the torque produced by seventh harmonic and fundamental torque. The torque produced by seventh harmonic reaches its maximum positive value just below 1/7 of synchronous speed ns, and at this point slip is high. At this stage, motor does not reach up to its normal speed and continue to rotate at a speed which is much lower than its normal speed. This causes crawling of the motor at just below 1/7 of synchronous speed and creates the racket. The other speed at which motor crawls is 1/13 of synchronous speed. Click Next to continue. Cogging of induction motor. Click each to know more. This characteristic of induction motor comes into picture when motor refuses to start at all. Sometimes it happens because of low supply voltage, but the main reason for starting problem in the motor is because of cogging, in which the slots of the stator get locked up with rotor slots. As we know that there is a series of slots in the stator and rotor of the induction motor, when the slots of the rotor are equal in number with slots in the stator, they align themselves in such a way that both face to each other, and at this stage the reluctance of the magnetic path is minimum and motor refuses to start. This characteristic of the induction motor is called cogging. Apart from this, there is one more reason for cogging. If the harmonic frequencies coincide with the slot frequency due to the harmonics present in the supply voltage, then it causes torque modulation. As a result, cogging occurs. This characteristic is also known as magnetic teeth locking of the induction motor. Click Next to continue. How can we overcome cogging? There are two methods to overcome cogging as follows. 1. Number of slots in rotor should not be equal to the number of slots in the stator. 2. Skewing of the rotor slots. That means the stack of rotor is arranged in such a way that it angles with the axis of the rotation. Click Next to continue. Click Next to continue. Let us look at significance of locked rotor current. Motor is not equipped with any facility to prevent it from self-destruction. External means must be provided for motor protection. If manufacturer says a motor is good for locked rotor ampere for 30 seconds, user must provide means to protect motor beyond this period. Click Next to continue. Let us see different mounting positions of induction motor, which are foot mounting, flange mounting and face mounting. Click each to see the images. Click Next to continue. We classify starting methods for squirrel cage induction motor into two following types based on voltage. 1. Full voltage starting method and 2. Reduced voltage method. Click each to know more. Under full voltage starting method, DOL or direct online method is used prominently. In this method, we directly switch the stator of the three-phase squirrel cage induction motor onto the supply mains. The motor at the time of starting draws very high starting current, which is about 5 to 7 times the full load current for the very short duration. The amount of current drawn by the motor depends upon its design and size. Click Next to continue. Now let us derive the expression for starting torque in terms of full load torque for the direct online starter. We have various quantities that involved in the expression for the starting torque as written below. We define Ts as starting torque, Tf as full load torque, If as per phase rotor current at full load, Is as per phase rotor current at the time of starting, Sf as full load slip, Ss as starting slip, R2 as rotor resistance, Ns as synchronous speed of the motor. Now we can directly write the expression for torque of induction motor as, from the help of the above expression, we write the ratio of starting torque to full load torque as, here we have assumed that the rotor resistance is constant and it does not vary with the frequency of the rotor current. Since Is equals to 6If and Sf equals to 3% or 5%. Therefore, using these values in the two equations, we get Ts equals to 1.8 Tf. Ts greater than Tf will always be greater than full load torque. Click Next to continue. Under reduced voltage method for starting squirrel cage induction motor, we have following three methods. 1. Stator resistor starting method. 2. Auto transformer starting method. 3. Star delta starting method. Click each to know more. In this method, we add resistor or a reactor in each phase as shown in the diagram, that is between the motor terminals and the supply mains. Thus, by adding resistor, we can control the supply voltage. Only a fraction of the voltage X of the supply voltage is applied at the time of starting of the induction motor. The value of X is always less than 1. Due to the drop in the voltage, the starting torque also decreases. We will derive the expression for the starting torque in terms of the voltage fraction X to show the variation of the starting torque with the value of X. As the motor speeds, the reactor or resistor is cut out from the circuit, and finally the resistors are short-circuited when the motor reaches to its operating speed. Due to heat loss at the stator resistor, this method is no longer used. Now we can directly write the expression for torque of the induction motor as, click Next to continue. The auto transformer is a step-down transformer. Hence, it reduces the per phase supply voltage from V1 to XV1. The reduction in voltage reduces current from Is to XIS. After the motor reaches to its normal operating speed, the auto transformer is disconnected and then full line voltage is applied. Now we can directly write the expression for torque of the induction motor as, click Next to continue. This method is used for the motors designed to operate in delta-connected winding. The terminals are marked for the phases of the stator as shown in the diagram. Now let us see how this method works. The stator phases are first connected to the star by the help of triple pole double throw switch (TPDT) switch as shown in the diagram. The position is marked as 1. When the steady state speed is reached, the switch is thrown to position 2 as shown in the above diagram. Now let us analyze the working of the above circuit. In the first position, A, B and C terminals are short-circuited, hence forming a star point, neutral point, and motor starts in star connection with reduced per phase voltage. In second position from the diagram, the terminals A, B and C are respectively connected to capital A, capital B and capital C, forming a delta connection and runs motor with per phase voltage. Now we can directly write the expression for torque of the induction motor as next to continue. Click next to continue. Click next to continue. Let us now learn about the starting methods of slip ring induction motor. Here is the trick. We can employ all the methods that we have discussed so far for starting of the squirrel cage induction motor to start the wound rotor motors. Let us look at one of them, which is addition of external resistances in rotor circuit. Addition of external resistances in rotor circuit will decrease the starting current, increases the starting torque, and improves the power factor. The circuit diagram is shown below. Click arrow to continue. The three slip rings shown are connected to the rotor terminals of the wound rotor motor. At the time of starting of the motor, the entire external resistance is added in the rotor circuit. Then, the external rotor resistance is decreased in steps as the rotor speeds up. However, the motor torque remains maximum during the acceleration period of the motor. Under normal condition, when the motor develops load torque, the external resistance is removed. Click next to continue. Post-assessment. Thanks. You have completed the course.